This is not the last topic, the second to last topic. We're at the transport layer, so we've gone through physical layer, data link layer, IP. The Internet Protocol is at the network layer. It's about getting data across the Internet via routers. We're now at the transport layer, which is about getting data from our source application to our destination application. So we're going to look at what is a transport protocol. Then we're going to look at two examples. The first one will be UDP, which we'll go through quite quickly today because it's very simple, and then spend a bit more time on TCP, Transmission Control Protocol. What is a transport protocol? What's the role of the transport layer? We want to allow applications on different computers to communicate across the Internet. An application on your computer wants to communicate with an application on some other computer anywhere in the Internet. So the transport protocols are about getting data between applications. And in particular, our software applications, we know, are made of software processes. We run a process on the computer, on the operating system. In fact, some applications may have multiple processes. So it's about getting data between application processes on the source host and on the destination host. Transport protocols, and even the higher layer application layer protocols, do not care about what happens across the Internet, that is at the routers and the intermediate devices. They're just a set of rules for communicating between the source and destination host. So here's our source computer, and we have an application running on that. And here's our destination computer. Our goal is to allow those two applications to communicate. And here's our Internet, which is made up of routers and other devices. IP was about getting data via these routers from source to destination. Transport protocols, we're going to ignore what happens in between the source and destination host and focus on communications just from here to here. And therefore, sometimes transport protocols are referred to as end-to-end or host-to-host communications. It's just about how do you communicate between the end devices. Of course, the data goes via these routers, but from the transport protocol's perspective, that is up to the Internet Protocol to deal with how to get the data via those routers. There are different types of transport protocols available in the Internet. The two main ones in use today are TCP and UDP, and that's what we'll talk about in this course. There are several others which are really built for very special purposes. But most of the applications you use today, your web browser, your voice client, Skype, instant messaging client, most of them use TCP. Some of them may also use UDP. So we'll talk about those two protocols. TCP is the Transmission Control Protocol. It's controlling transmissions between applications, source and destination application. And it's quite complex. It does most of the things that IP does not do. Remember, all that IP does is delivers data from source to destination via the routers. IP, the Internet Protocol, does not have any error control. If we send an IP datagram and it doesn't get to the destination, there's no concept of retransmission. But sometimes, and many times, our applications need such a service. If I want to transfer an email a 1 megabyte email from here to here, I want to make sure that the full 1 megabytes are delivered to the destination as in the same form as how they were sent. So if one of the packets is lost, then we need some retransmission scheme. Rather than me implementing this retransmission scheme in my application, so if I write my own email application, one option I could do is implement some retransmission schemes in the application. That is, I send the email. If I don't receive an acknowledgement, I could retransmit. But many applications need this same service of retransmissions because many applications want the data to be reliably delivered to the destination. So the focus or the role of TCP, one of the roles of TCP is to provide this reliability using error control. That is, you use your application. If you want to make sure the data is reliably delivered to the other side, use TCP. TCP implements some rules such that if something is lost, it will retransmit. So TCP includes error control for reliability. It's a connection-oriented protocol. We establish a connection before we transfer the data. It has flow control. If this application is sending very fast and this is a slow computer with a limited amount of memory, then we could overflow this destination computer, the memory there. So TCP implements some flow control that will slow down the source application. And congestion control. If this application sends very fast, then possibly what may happen is that many packets are coming into these routers and maybe one of the routers becomes congested. That is, it's receiving a lot of data from this source and maybe from other sources, and it cannot send out fast enough. That is referred to as congestion inside the internet. If a lot of traffic is coming in, but it can only send out at some speed, then it will start to drop some of that data, and that's a bad thing for our application. So TCP includes some mechanisms such that if we notice there's congestion in the internet, slow down sending to try to reduce that congestion. And the congestion control and flow control are quite complex mechanisms. We will not cover congestion control in this course. TCP is a very complex transport protocol, but used by most applications. UDP is a very simple transport protocol. It effectively does the same as IP. It takes your data, sends it. If it gets there, good. If it doesn't, too bad. UDP will not try to retransmit. It has no concept of flow or congestion control. It is an unreliable, connectionless delivery mechanism. So UDP is an option that we can use if we want a very simple transport of our data between applications. Effectively, it does the same as IP, one extra mechanism. We'll cover both of them. There are other transport protocols. One thing that's common to all of these transport protocols is how they use addressing. And how do we use addresses to identify applications? And they use this concept of a port number. And we've spoke about a port number early in the course. A port number is a port is some abstract view of the endpoint for communications. Our applications are the endpoints. They're the things that they want to communicate. Or more specifically, a software process is the endpoint. We have a process running on your computer, and that process on the computer is the endpoint for communications. So we use port numbers to identify these processes, because on your computer you may run multiple processes. So when you receive data, somehow your computer needs to know which process does this data go to. Does it go to your web browser, your Skype client, your instant messaging client, or whichever? And that's what we use port numbers for. Most internet applications follow a client-server model for communications. We have two applications that communicate with each other. One of them can be designated as the client application and the other the server application. And the way that they communicate is that the client initiates communications. So it contacts the server saying, I want to communicate with you. And the server then responds if it's willing to communicate with a client. And then they can start the communications. So a client initiates communications. What does a server do? A server simply waits there until some client initiates communications with it. So you can think a server does nothing. It's running. It's a process that's executing. And it does nothing until a client initiates communications with that server. And the common one example that you know is a web browser and a web server. Where a web browser is, we can think in the simple view, is a software process running on your computer, and that's a client application. And a web server is a software process running on some other computer, and that's the server application. And web browsing involves communicating between the two. That's the application, the overall application. So what does the server do? It's sitting there executing on some computer, waiting for a client to contact it. So maybe this is the ICT server, the computer somewhere in the other building, ICT.SIT is a domain name and it has an IP address, 10.10.6.11. So that computer has an IP address. It's on the internet. And on that computer there's an application running, which is the web server, just a piece of software. It's sitting there doing nothing until a client contacts it. So your client, in this example, is the web browser on another computer. Let's say on my laptop, has some IP address, 10.10.6.1, and when I start my web browser, I've got some application running on my computer and type in some domain name into the address bar in my web browser, then that triggers the web browser to contact the web server. In fact, the domain name that I type in, maybe ICT.SIT, so on, maps to an IP address, such as 10.10.6.11. So I type in the destination address of the device that I want to contact, and that triggers our client to contact the web server. For this to work, the client application needs to know the address of the server application. And there are different types of addresses or different types of information that identify the server application. We need to know the IP address of the device. Okay? If I want to contact the ICT web server, I in fact need to know the IP address of the computer that hosts that web server. And in fact, the way that works is using the domain name system. In my browser, I type in the domain name in the address bar. The domain name actually maps to an IP address. So ICT.SIT maps to some IP address. So alternatively, I could type in an IP address in the destination address. If my internet's working. So I just connected to that server, okay? I can reload. So this is me, the user, telling my client application the destination IP address by either typing in an IP address like this, or typing in a domain name, and then there's something else is used, the domain name system, to find the corresponding IP address. We'll talk about the domain name system in next week, in the last topic. So I need to know the IP address of the device hosting the web server. But that device, this computer, 10.10.6.11, may be running many pieces of software at the same time. It may be running a web server, an email server. In fact, it may be also running a web browser. There may be someone sitting at it running a web browser. On that computer, there's potentially many applications running at the same time. So there's two other identifiers that we need to know to deliver this data to the web server, not to the email server. We need to know what transport protocol is being used, and that's identified by the protocol number. So an application, or a pair of applications, client and server, will use the same transport protocol. Our web browser and web server will use TCP. Other applications may use a different transport protocol. So we need to know what transport protocol is being used, TCP in this example, and each transport protocol has a protocol number assigned to it. TCP is number 6, UDP 17, and there are others. There's a list on this at this URL, the official list of those protocol numbers. And in addition to the transport protocol, we need to know what application process on this destination computer we want to contact. That is, my web browser needs to send something to an application on another computer. The other computer is identified by the IP address of that computer. The application on that other computer is identified by the port number. So we need to know the port number of the web server. And it turns out that most web servers, by definition, will use a fixed port number 80. So a port number identifies an application process on a computer, on a host. There are 16-bit numbers. Some of them are defined and some of them are chosen dynamically. So for my client to send something to the server application, I need to know what is the IP address of the host of that server application, what is the transport protocol being used, TCP in this example, and what is the port number of the server application itself. And if I know that information, I can send data to that application, and if I include information about my client application in the first message I send, the server will learn my address. So it's important to know the server's address, and then we can learn about the client's address. We'll say a bit more about the structure of port numbers. I'll use the next slide to illustrate that in a bit more depth. This shows a source host, destination host, in a bit more detail with the layers. We have some applications running on the source host, a web browser, instant messaging client, some voice over IP client, some other software running. And on this destination host, we also have multiple applications running, a web server, some instant messaging software, and our voice software. So maybe at the same time, I would like to contact the web server, send an instant message to the instant messaging client here, and also be talking in a voice call between these applications. And this shows the stack the data link and physical layer protocols, whichever is used by the network technology here, IP, and above that the transport layers, or the transport layer with different example protocols. In this case, TCP, UDP, and in fact ICMP is considered from a transport layer perspective here as well. Focus on TCP and UDP. Different applications use different transport protocols. In this example, our web browsing application using TCP, instant messaging using TCP, our voice application using UDP. When my web browser wants to communicate with a web server, I need to know the IP address of the server, the server computer or the server host, e.g. 10.10.6.11. I need to know the transport protocol we're using, and by default, web browsing applications will always use TCP. In fact, we use the number to represent TCP, the number 6. And I need to know which application on this destination host 10.10.6.11 do I want to communicate with. Well, of course, by default, a web browser wants to communicate with a web server. And a web server, by default, uses a port number and port number 80. So I will create some message to send. TCP, it will be sent to TCP. We'll see what TCP does. One thing TCP will do is include a header which includes the destination port number. TCP will go to work, send it to IP. IP will create an IP datagram, include a header, and if you remember back to the IP datagram structure, of course it had a source and destination address and a protocol number field. So we would include this value 6 in the protocol number of the IP header. So these are in the IP headers, IP header, and this is in the TCP header. We'll see the exact structure of this in a few slides. Just to add a few more things here. We also would include in the IP header a source address, let's say 10.10.6.1, which is in the IP header. That will be useful in a moment. That is the address of this host, and a source port number. The port number used by my web browser. My web server has a port number 80. My web browser also has a port number. The port number for your web browser is usually not fixed. It is dynamically assigned by your operating system. Let's give it a value. If my web server is port number 80, let's say 50123. I'll talk about the significance of the numbers shortly. Let's go through this example. So my browser has a port number as well. That's the source application. And that would be included in the TCP header. And we'd create a TCP segment, which is put into an IP datagram and eventually sent across the internet through our routers. IP will deliver it. If everything works well, IP will deliver it to the destination host, to 10.10.6.11. Once it's received, the destination host looks at the transport protocol field and determines to send the data to the corresponding transport protocol. That is, it receives this segment, or the segment containing this information. It's destined to 10.10.6.11, that is, it's reached the destination. So IP removes the header and sends the contents to the corresponding transport protocol identified by this number. Send it to transport protocol 6, which is TCP. So when IP receives, it knows not to send to UDP, not to ICP, ICMP, not somewhere else, send to TCP based on the protocol number field. When TCP receives, it will process that data, remove the header, and it will know to send to the web server process running on this computer, not the instant messaging process, based on the destination port number. So send to the web server software, port 80, the contents of the message, the data. So the port number identifies the application, protocol number identifies the transport protocol, IP address identifies the host in the internet, the device. Of course, most applications involve two-way communications. I send something from the browser to the server is going to send something back. And because we included the source IP address and the source port number, and the protocol number is the same in both directions, we can send a message back because we just set the destination IP address to be 10.10.6.1 and the destination port number to be 50123. So the server learns of the IP address and port number when it receives the first message. And that's why it's important for servers to have a well-known port number, a number that your browser or your client knows about, whereas clients can have dynamic port numbers, numbers that are randomly assigned by an operating system. They can change because the first message always goes to the server. Therefore, we need to know the port number of the server. The second message coming back goes to the client, but the server learns the port number from the first message. So we can think of 5 things that identify our communications in the internet. Source and destination IP address identify the hosts communicating. Protocol number identifies the transport protocol being used. Both endpoints use the same transport protocol. And source and destination port number identify the applications that are communicating. Those 5 identify our communications in the internet. The port numbers are divided into different spaces. That is, some numbers are used to identify what's called well-known ports. These are used for common servers used in the internet. Port 80 is in this range of 0 to 1023. So these first 1000 port numbers are assigned and are usually fixed for different applications. Port 80 for web server applications, port 25 for email server applications, port 23 for other applications. I can't remember the numbers. And many of those numbers are assigned for different applications in the internet, and they are fixed. The lists of the assignments can be found here. They are fixed because your client needs to know them in order to communicate with that server. From 1024 up to 49,151 are what's called the registered ports. And in fact, they are often given to servers as well. You start your own company and you create your new internet application. And it needs to run a server. It's a new internet application for some game that you've created. There's a server for the game. So you want everyone that accesses your game to know the port number of your server. So you would go and register that port number, a port number that's not currently used, one within this range, maybe 40,361. You'd register that, it'd be added to the list, and then anyone who wants to contact your server, any game that needs to contact your game server, knows that port number The remaining port numbers, 49,000 up to 65,000, are typically used for clients. The client application, when it starts, the operating system gives it a port number, usually within this range of the dynamic or private ports. So when you start your browser, your OS gives it a port number. And in fact, if you start multiple tabs on your browser, you may get different port numbers for each set of communications you create from your browser. So we don't know these in advance. We can think they're randomly chosen from some range, so long as they're not currently used by your computer. Note that the port numbers are unique on a particular computer. Two different applications must use different port numbers on this computer. But of course, we can have many computers running web servers using port number 80. The concept of port numbers and protocol numbers are common to UDP and TCP and other transport protocols. You could program, or you could tell, if you could program your operating system, you could tell it to assign a particular port number, yes.
I don't want to use ITS323 for web browser. I change to another.
Your web browser doesn't use port number, your web server uses port 80. So you can specify what port number you want to contact.
The server specifies.
By default, a web server uses port 80. But there's nothing to stop me from running a web server using port 81. So if I run a web server using port 81, that's fine. The problem is that most web browsers assume to contact port 80 because they need to contact a web server. So if you want to tell your web browser to contact not port 80 but port 81, you include the port number in the address. It won't work here. I would type that in. Tell my web browser to contact 10.10.6.11 port 81. And that would contact a web server running on port 81. It won't work because there's no web server running on port 81 on 10.10.6.11. So by default, your web browser includes port 80. If you want something else, you need to specify that. Let's contact let's try another server, our IT server. What was the name of? Even better, what's someone's ID? Who has a website from who created a website for the assignment? Put your hand up. Who was one of the people who had the URL? Put your hand up. What's your 522 78? Hang on. 78 0728. Correct? Okay. 10.10.6.10 is the IP address of the IT server. This just shows the connections that my computer has at the moment. My address is 10.10.286 of my laptop. I just contacted 10.10.6.10 and I contacted the port number of the web server, port 80. There are multiple connections here. The ones we're looking at are between 10.10.286 and 10.10.6.10, the first one, for example. This just lists the set of recent communications from my computer to some foreign computer, some remote computer. So my computer 10.10.2.86, an application on my computer using port number 47356. That is my web browser. My web browser was assigned this port number for that set of communications. Contacted some foreign address, 10.10.6.10, the IT server, an application on the IT server, a web server application, port 80. I established a connection from client to server using the protocol TCP. In fact, I established multiple connections at the same time because most likely his website, to download some of the images, I created parallel connections from my browser to the server. And some of the other ones are listed here. So now let's look at quickly how UDP works and then some more detail about TCP. UDP is the User Datagram Protocol. It's an unreliable, connection-less transport protocol. Unreliable in that it does not attempt to provide retransmissions to fix errors. You send a packet across the internet. If it doesn't get to the destination application, too bad. It will not try to retransmit and fix it. So our delivery is not 100% guaranteed. Connectionless, we do not establish a connection between source and destination. We'll see TCP is connection-oriented. We do establish a connection. And it's very simple. It takes data from the application and puts it into a UDP segment and sends it to IP. If we can illustrate that, our client application creates some data. That it wants to send to some destination application, sends to UDP. UDP takes the data, creates a UDP segment. We'll see the structure. It has a header and the data. So it puts the data inside a segment with a UDP header. The UDP header has 4 things. 4 fields. The source port, that is, it will include the port number of our application. Let's say it's using 51112. This client application is the source port. The destination port, the application we're wanting to communicate with, whatever that is. The data may be of varying length. So it specifies what's the total length of this segment. We have 8 bytes plus all the bytes of the data. If our header is 8 bytes and our data was 1,000 bytes, then our length is 1,008 bytes. And a checksum, which is our error detecting code to determine, for the receiver to determine if there are any errors in the data that was transmitted. Although we have a checksum, so if I transmit this data across the internet and it arrives and the checksum indicates that there are some errors, some bit errors, we at least know that there were some errors, but UDP makes no attempt to fix those errors. There's no ask for a retransmission. So the checksum is used by the receiver to determine if what's received is in error or not. For example, we've spoke about parity checks, CRC as a checksum algorithm, and there are other algorithms. So they're the 4 fields of the header, and UDP creates this and sends it to IP. IP will put this into a datagram and send that datagram across the internet. And it's eventually received. IP, inside the IP header will be the protocol number, number 17, says to send the data to UDP. So UDP will receive this at the destination, remove the header, and send the data to the application. Based upon the destination port number, which tells us what application to send it to. So that's all that UDP does. Just put the data inside a segment and send it. It provides a checksum over the packet for error detection.
So no tracking, so cannot, no tracking.
No
Tracking process.
No tracking, no sequence numbers. We just send it and forget about it. That is, we receive some data, we send, and that's it from the perspective of UDP here.
Like ordinary email.
And like IP, that's what IP does. We receive data, send it, and make no attempt to deliver it, no further attempts to deliver it to the destination. It's very simple. It's very basic in that we may lose segments. I may send 10 segments across the internet. Let's say the amount of data I had was 10,000 bytes, and they've been split by the application into 10 segments of 1,000 bytes. So I would send 1, 2, 3, up to 10 segments across the internet. Some of them may be lost. That is, of the 10 that I send, maybe I only receive 8. Some of them may arrive out of order. I send segment 1, 2, and 3. It arrives as segment 2, 3, and 1. Some of them may be duplicated. Something goes wrong in the internet. I send segments 1, 2, and 3, arrive as 1, 2, 2, 3. One segment arrives twice. That's possible. Not very common, but it's possible if something goes wrong in the internet that we get 2 copies of the one packet. And they may arrive in error. We can detect that with a checksum at UDP. But it's up to the application to fix that error. Because it's very simple, it's used by applications that require simplicity. Maybe you have an application for an embedded device, a projector, and you want to use IP and an application to control the projector. That is, it's running a simple application on the projector, and I can contact that from my laptop. Because we don't want to use too much processing on the projector, and we don't have much memory to implement the application, using UDP may be a nice approach because it's a very simple and small implementation of a transport protocol. TCP is much more complex. So if we need simplicity, we may use UDP. UDP does not offer reliability, so applications that don't need reliability may make use of UDP. I'm in a voice conversation using Skype, and with voice, if I send some data and not all of the data arrives at the destination, then the receiver can still understand what I'm saying. So that doesn't rely on reliability. So UDP may be used for voice and video applications. Also, because such applications usually require a small delay. We just send the datagram. In TCP, we'll see we may send a datagram, we may have to wait for acknowledgements before we send more. TCP may introduce a larger delay in our communications. UDP should have a shorter delay. So if our application requires a small delay, we may want to use UDP. So if we want to be fast, efficient, small in our implementation, then UDP may be an option. So let's compare it to how complex TCP is. segment. TCP is used by many more applications than UDP because most of the things that we do on the internet, we need reliable communications. I download a file, I must receive all bytes of that file with no errors in order to use that file. I send an email, the email must be delivered with no errors. TCP provides that service for us. It's the most commonly used transport protocol today. So most of the applications you probably use on a daily basis use TCP. Web browsing, file sharing, instant messaging, accessing databases remotely, build your own application using Java. Most likely you use TCP unless you have a special purpose for UDP. What does it do? It's a connection-oriented protocol. Before we transfer data from client to server, we establish a connection. We send some special message to the server saying, I want to communicate with you, and the server will respond saying, yes, you can communicate with me. We establish a connection. And we'll see that that has different purposes to do that. Once we establish a connection, we have a full duplex connection. Although the client initiates communications saying, I want to connect to the server, if the server says yes, once they're connected, we can send data in either direction. Client can send data to the server can send data back to the client. We talk about a full duplex connection. It provides error control, retransmissions. If I transmit data and it doesn't get there, eventually I'll retransmit. We get acknowledgements coming back. Flow control, if my destination is very slow and I send too fast, the destination will tell me to slow down. Congestion control, if the internet is becoming congested, in particular the routers, and they're starting to fill up the buffers at the routers, then my source application may eventually slow down so the internet becomes less congested. And stream-oriented, we'll explain this in a bit more depth shortly, but that means we treat the data that comes from the application as just a set of bytes, a sequence of bytes or a stream of bytes. Sometimes our application may generate a message, send it to TCP, and then shortly later generate a second message and send it to TCP. From TCP's perspective, those two messages are not distinguished. They're just treated as a sequence of bytes. So it may not send them as two separate messages across the internet. It may send them as one. We'll see that shortly. And we'll also, when we talk about that, talk about what we mean by buffered transfer. This is our TCP segment. More complex than the UDP segment. We have a header of 20 bytes. We can have some optional fields in the header. We will not talk about them. And then we have our data. So that's our TCP segment. And there's just one type of TCP segment. We have a source and destination port, same as UDP. We identify the application that the data came from and where it's going to. Because we have flow control, congestion control, and reliability, we use sequence numbers. We've seen this concept many times. When we looked at go back N, the sliding window mechanisms, every segment that we sent had a sequence number, 1, 2, 3, 4. We have a field to store that sequence number, a 32-bit field. And in fact, we send segments and expect acknowledgements to come back, saying, thank you, I've received that sequence number. So in fact, we have a field also for an acknowledgement number. Because we may have options in the header length may vary. It may be more than 20 bytes. So there's a field to indicate the length of the header. Some fields are not used, they're reserved for future use. We'll come back to the flags in a moment. We use flow control. With flow control, the receiver tells the sender how much it's allowed to send, such that it doesn't overflow the buffer at the receiver. And we use a windowing concept, sliding window. We cannot send more than the window allows. In TCP, the window may change. So we have a field in the header that the receiver says, this is what my window is right now. You cannot send more than this. That's used in flow control. We have a checksum to check if there's any errors in the segment. Urgent pointer is used for special cases if we want to deliver the data to the destination application with some priority. Some optional fields may be used, and then the data. There is one type of TCP segment, but the TCP segment may have different meanings, and those meanings are determined by the flags. Don't draw this diagram, you've seen it before. We've seen these diagrams when we looked at flow and error control. We send some data, we get an ACK in response. In fact, sometimes we include sequence numbers. Data 1, ACK, what number? Not 1. Anyone else want to guess? If I send data 1, what do we know? What do we expect the acknowledgement number to come back? 2. We always think of acknowledgements as saying, if I've just received data 1, I send back an acknowledgement saying the next one I expect is 2. That's the concept that we've seen in previous topics. Flow control, error control. We have 2 different types of frames or packets. In TCP, there's just one type of segment. It's shown here, it's structured here. But the flags can take values that indicate the meaning of the segment. A flag is a 1-bit value. If the value is 0, then the flag is off, and if it's 1, the flag is on. The list of flags are given here. For example, there's an ACK flag. So if we want to send data using TCP, we send a TCP segment, which has the header and some data. So in this case, it includes data. And it would include a sequence number, let's say SN, let's say sequence number 1. So that's what we'd expect. We send a TCP segment including data. If it includes data, we can say it's a data segment, or it's a segment containing data. And then we want to send an ACK back. Then we send another TCP segment, but we set the ACK flag to be true, to be on. So this message that we send back is a TCP segment. That is, it's the same as this. It looks like this. It may not have data. It may be just the header. So it's possible to send a segment without or with 0 size data. But of the flags here, one of them, the ACK flag, is set to true or set to bit 1, which really means this TCP segment is an ACK segment. It's acknowledging something that we've just received. And we know from the header, we have a field for a sequence number. We've received sequence number 1. When we send an ACK, we would set the acknowledgement number to some value. So maybe it's 2. We'll see later it's more complex than that, the acknowledgement number. So these are both TCP segments. There's no special types of segments, but there are different meanings of segments. This is a segment containing data. This is a segment which is an acknowledgement because the ACK flag is set to 1. And yes, if the segment contains data, it's data, a data segment. Because we can piggyback now. This segment is an ACK for this, but if we include some data in it and set a sequence number, this segment is both an ACK for the previous message and a data going in this direction. That's the concept of piggybacking, sending one message which has two different meanings, an ACK and some data.
And the TCP segment encapsulates data and acknowledge together or piggyback.
This is the TCP segment. So the data would be included here. The ACK flag would be set to 1. The sequence number would be set to 9. And the ACK number would be set to 2.
So if it's not a piggyback, the same size is still, the size is still the same.
Yeah, it's still this structured in this way.
If they have data acknowledge, it's 0 and no acknowledge.
Yeah. So in this first one, in fact, the ACK flag would be set to 0, as would all the other flags there. If we don't specify the value of the flag, then we'll assume it's 0.
So it's the same container size?
The segment's the same. All segments are the same header structure. That's the point here. They don't have different types of segments, although they have different meanings. And there are different types of flags. One of them we'll see is the ACK flag. We use that if we're acknowledging some data. We'll see shortly there's a synchronize or a SYN flag to used in the connection setup to synchronize some sequence numbers. We can use a FIN or a reset flag to close a connection. Remember, we set up a connection, transfer data, then close a connection. These are used to close connections. And there's some others we may see as we go through. If they have the value 1, then it means that that feature is being used, or that meaning can be interpreted as being used. We include sequence numbers. We use them for error control, flow control, congestion control. So we know how sequence numbers are used for flow and error control already. We send a sequence number. The ACK tells us what we've successfully received. The initial value of the sequence number does not have to be 0. Up until now, we've assumed, okay, what's the first value of a sequence number? 0. In TCP, when we establish a connection, we agree upon the initial sequence numbers. Both sides choose an initial sequence number, the ISN. Remember, it's a full duplex community. We will see that in a few slides. How do we set up the connection? We'll show how to do that. So we have initial sequence numbers, and you can think that's the first value, and then we increment from there. So we'll go through that in a moment. Sequence numbers in each direction are independent. If I'm sending data to the server, I'm using one set of sequence numbers, maybe 1, 2, 3, 4, 5, depending upon my initial sequence number. If the server's sending data back to me, it can be used a different set of sequence numbers, 3043, 3044, and so on. The sequence numbers in each direction are independent of each other. They don't have to be the same. Each byte of data has a sequence number, and it's relative to the initial sequence number. We'll see that shortly. We'll see an example of sequence numbers when we go through how do we set up a connection. We're going through reasonably fast, but we'll see once we've gone through the different mechanisms, you'll see them all come together. TCP is connection oriented. We establish a connection, transfer the data, close a connection. When I showed you this, my computer had 7 connections at that point in time between different applications and different destinations. And the connections, you can see, were in different states. Some were established, that I had already established those connections to the destination. One was in a state of time wait, which is a special state, meaning we've transferred the data, it's waiting to close that connection. It's eventually going to close. This was, what, 20 minutes ago that I run the command. If I run the same command now, only 2 connections are established between my computer and destinations. Are they the same? One's the same, and both of them are the same. So my computer is doing something in the background of transferring data. The other connections that I connected to 10.10.6.10 when I transferred data from the web server have been closed. I didn't close them. They time out after some time. If there's no data transferred after 2 minutes, they will close automatically. Or they'll enter a time wait state and then eventually close. So we open connections, transfer data, close connections. How do we open connections or establish connections? First, what's the purpose? Why do we establish a connection? It allows each device or each application to know whether the other exists. Okay, that's very simple. If I try to connect to a web server and the web server is not up and running, then the connection will be unsuccessful. That's a very basic thing. It allows each side to exchange or negotiate values that they're going to use for the data transfer. Specifically for TCP, we need to tell each other our initial sequence numbers. I'm going to choose an initial sequence number, 3042. I need to tell the server that value. The server chooses initial sequence number, 173, and it needs to tell me that value. That happens when we establish a connection. Once we establish a connection, we may allocate resources for that connection, some memory for the data transfer that's about to occur, some buffer space. So every time we establish a connection, we use some memory of our computer for that connection. And in fact, you'll see that next semester, that's one of the security flaws in doing that, is that a denial of service attack can be applied. Many people establish connections to the one server. For every connection, it allocates some memory. Eventually, it will run out of memory. And once it runs out of memory, it may crash or it may not be able to do anything. That's another topic. How does TCP establish a connection? It uses a concept called a three-way handshake. A handshake to agree upon the parameters. Three-way in that we send one message to the server responds, and then one third message comes back. We'll see there are 3 messages. We will not discuss it, but a two-way handshake is not used because it will not work in some cases. You'll see in the textbook it explains why. This is the three-way handshake. 3 messages. 3 TCP segments are sent to establish the connection. Stay with us for 15 minutes. You'll need this. A is the client that's initiating the communications. B is the server. Each of these messages are TCP segments. What happens is that the client, A, wants to communicate with B, so it sends a TCP segment. It chooses an initial sequence number. ISN A. A chooses its own initial sequence number. Let's say 361. I'll just choose one for an example. And it sends a TCP segment to the destination B, including the initial sequence number. It includes the initial sequence number in the sequence number field. If we go back to our TCP segment, so we send a segment looking like this. There's no data in this initial segment. There's no data yet. We need to establish the connection. We set the source port for the port number used by application A, the destination port. We set the sequence number to the value of the initial sequence number that A chooses. ACK number doesn't matter. It can be set to anything. Of the flags, the SYN flag is set to true. SYN means synchronize. The steps that we're doing here are to synchronize the initial sequence numbers so that both sides agree upon the same initial, or agree upon each other's initial sequence numbers. So the SYN flag is set to true. The other flags are set to false, and we don't care about them. That's the first step. When B receives this first TCP segment, and it's often referred to just as a SYN segment, it's a TCP segment with the SYN flag to true. If it accepts, or if it's going to accept the connection, then it chooses its own initial sequence number. Independent of the number chosen by A. They don't have to be related. It stores the number that was chosen by A. Stores it in memory for later use. And sends back a response. And the response is a TCP segment, and it has two purposes. One is to tell A of ISN B. So in the same way, it sets the sequence number to be 1431, and it sets SYN flag to be true. So A tells B its sequence number, or its initial sequence number. B is going to tell A its initial sequence number. In addition, B is going to acknowledge the initial sequence number chosen by A, saying, thank you, I agree that you can use this sequence number 361, and therefore this one TCP segment, also we set the ACK flag to true. It's an acknowledgement of this. And we set the ACK number to what?
ACK number
is 2. And so the ACK number is going to be give me the number. 362. We just received a SYN segment, or a TCP segment with a SYN flag true and including sequence number of 361. Because the SYN flag is true, this is a special type of message, and it tells us the initial sequence number chosen by A was 361. So we acknowledge that, saying thank you, and the way that we do acknowledgements is say, what's the next number we expect? I received 361, the next number, 362. So ACK number equals 362. The ACK flag is true to indicate this is an ACK. Also, it's a SYN segment. It includes the initial sequence number of B. When A receives this, it sees the ACK. Okay, everything's okay. It receives ISN B. If everything's accepted, it sends back a final message. It acknowledges ISN B. ACK field equals, the ACK flag equals 1. This is an acknowledgement. ACK number equals 1432. we received 1431, ACK 1432. That's our connection establishment. Once that's done, they can start transferring data in either direction. A can send data to B, B can send data to A.
And how about SIN number?
In this last TCP segment, the other fields don't matter. That is, it's still a segment like this. It still has a source and destination port. The sequence number may have some value, but of no consequence. We could set it to the previous value that we set, 361. That would be the normal thing. But if I don't list it here, then it's of no use or of no relevance in the data, in the communication. It has a value, but the SYN flag is off. The SYN flag is 0. If I don't list the flag, then it's 0 here. So it's not a synchronized message. It's a simple ACK.
So the third
SYN
SIN flag is 0.
flag is 0 here, and as are all other flags except the ACK flag. And we get a SYN, SYN-ACK, ACK. That's the three-way handshake. Synchronize, acknowledge and synchronize and acknowledge. Once we've completed that, we can transfer data. We can send a segment that contains data. None of these contain data. But there's an option. We can piggyback data on the last message. A initiates the connection to B. We have data to send. We're allowed to include that data on this last ACK. So optionally, this last TCP segment could include some data, 1,000 bytes, for example, and it would include a sequence number. What sequence number? 362. So we don't have to have the data, but we can have it. It's allowed. 362, why? Initial sequence number 361, ACK saying thank you, I expect now 362. So the first data we send, in fact, should be 362, one more than the initial sequence number.
An option.
Including the data here is an option. Yeah.
And how about the second SYN-ACK? SYN-ACK and piggyback?
No,
No.
just the last ACK. If we keep going, of course, we can send data in either direction. If we didn't include it here, we could send a separate TCP segment with data. So we can piggyback the data on the last ACK, or send the last ACK and then send a separate segment. Either include it with the ACK or send it separately. Let's say we send it separately, just so I can continue on this diagram. So SYN, SYN-ACK, ACK, connection is now established. We start transferring data. A sends 1,000 bytes of data to B. Sequence number equals 362 because we chose an initial sequence number of 361. So the first sequence number we'll actually use for the data is 362. SYN is now finished. The SYN is for synchronizing sequence numbers because that's the part of connection setup. Connection setup, we want to tell each other what initial sequence number you choose to synchronize them. After that, no longer use the SYN flag. Now we just send a TCP segment with all flags set to 0. It's just data. B wants to acknowledge that. Sets the ACK flag to 1. It's an acknowledgement. Sets the ACK number. what's the ACK number for the A has sent 1,000 bytes of data to B. Sequence number 362, B sends back a segment with the ACK flag true and an acknowledgement number of 1431 wrong. Anyone else? 363 wrong. No. So this is a new thing. No. So one answer was 1432. No, this sequence number 1431 and onwards is used just for the data in this direction. Remember, we have data going in both directions. For the data from A sends to B, we start from 361. So the first piece of data, 362. And keep increasing. For data that B sends to A, we would start from 1431, or in fact 1432. But here, we've just sent data from A to B, 1,000 bytes. Sequence number 362. B is sending back no data, just an ACK. Sets the ACK number. Normally we would, no. Normally we would think 363. Some people said 363. Okay, that's the way we normally think. We send the next value. TCP uses sequence numbers to count bytes, not segments. So you can think this data has 1,000 bytes. The first byte, sequence number 362. The second byte, 363. The last byte, so 362, 363, byte 1, byte 2, 1,000 bytes. Each byte has a sequence number. The first, 362. The last would be therefore 1361 with 1,000 bytes. ACK number 1362. That's the difference from what we've seen in the past. Sequence numbers count bytes, not segments. So it depends upon how many bytes in the data that we've successfully received. If I sent 2,000 bytes, not 1,000 bytes, ACK would be 2362. If I sent 50 bytes, it would be, what, 412, the ACK number. So the ACK number is related to the sequence number and the number of bytes received. So that's important. Other than that, it continues as we know with a normal send data, receive an ACK. And if we send data in the opposite direction, that's when we use the other initial sequence number. B sends 10 bytes of data to A. Sequence number 1432, ACK. Last question, what's the ACK number? Ten bytes of data sent with sequence number 1432. A sends back an ACK with ACK number 1. One 442, 10 bytes. 1432, 1433, up to 1441. Therefore, the next one would be 1442. So the ACK number depends upon the sequence number and the amount of bytes. And it means the next one we expect. That's the same as before. What's different now is that sequence numbers count bytes, not segments. And that brings us to the end of today. We'll continue with TCP next week. We'll have a quiz next week on something, anything. And we'll finish this and have a short coverage of applications. Enough for today.